unmute your microphone, please.
Yeah. Hello? Yeah, okay. Good morning, everyone. I'm Tang from LMU, SPIN PhD, and today I'm talking about the seismic anisotropy from 6 ground motion of ambient seismic noise. So maybe some of you just familiar with ambient noise. So the interaction between ocean waves and the solid earth can generate the two dominant microseismic noise. So secondary microseismic noise and the primary microseismic noise. So they have different mechanisms. So the secondary is mainly come from the interaction between ocean waves, and then the second step is also interaction with the solid earth. So the primary is just a directly interaction between ocean wave and the solid earth. So for this two dominant microseismic noise, what can we do in general? That is, and we have two stations. We can do the cross correlation between two stations. We can get the cross correlation function, and in general, we can just using the cross correlation function to do the velocity tomography, and like the right figure, and that is quite important and a very famous methodology. And then if we have another three kind of observation, the rotation just measures the rotated angle when during the medial deformation. So if we have another three rotation, what can we do in terms of microseismic noise? And also we have the seismometer that can directly interact the rotational motion. For example, the first one is the Jiren seismometer that only have one component and just associated with low wave. And another one is Rumi. It has three components. It can measure low wave and real wave. So yeah, we have the seismometer. So if we have the observation, what can we do? Yeah. And I will give two examples. The first example just based on single 6 station, just to estimate the noise source direction. And the second is we can use one pair of station just to do using the cross correlation technology to estimate the local seismic anisotropy. So if you look at the ocean wave height in different season, the left is the July and right one is December. You can find the ocean wave. It has a very clear difference. Yeah. So it is expected that the microseismic noise also could be the seasonal variation because of the ocean wave seasonal variation. So here we just want to use one single 6C station to estimate the noise direction. So the basic idea is just to do the cross correlation, calculate the correlation coefficient between the translation and the rotation. And we do a grid search in the back-azimuth domain. And we can find we have two parts. The first part is the negative part of the correlation coefficient. And also another part is a positive part. So we can find the real back-azimuth just in the central point of the positive part correlation coefficient. So this is quite simple to estimate the noise source direction, even also for earthquake waves. So, and we find two seismic stations. The first one is Southern California region. So in this region, there's no rotational, no broadband rotational seismometer. So we select a small seismic array, which means the small seismic array only have 500 meters aperture. So this is compared to the wavelength is much smaller, which means this small array can be regarded a point measurement. And also we select another Jiren seismometer in Germany, and we use these two stations to estimate the noise source direction. So first look at the Jiren data in Germany. So the left one is low wave. Yeah, as I said, yeah, the Jiren only one component, just associated with the low wave. So the left figure just shows the noise direction of secondary microseismic low wave. So they mainly come from the 300 degree, which means it's come from the north part of Atlantic Ocean. And also the longer period, it also mainly comes from the north direction. Yeah, but it is a very clear seasonal variation. And if you look at the PFO is in Southern California. So the left figure just shows the secondary microscopic noise. The secondary microscopic noise is just mainly come from the west direction, southwest direction, 225 degrees. So this source because of there's two small ocean, two small where can generate a strong interaction and in this direction and can generate very, very strong really well. So for the right figure, it's a longer period really well. So the longer period is the mechanism because of the direct interaction between ocean whale and the solid earth. So in the winter, you can see in the winter, it's mainly come from 300 from 300 and 350 degrees. It's come from the north part of Atlantic Ocean, Pacific Ocean, and also 45 degrees mainly come from the north part of Atlantic Ocean. And in the south, in the summer, it is mainly come from the southwest direction. Yeah, it is because of the two differences because of the different mechanisms. Yeah. And we use a single 6C seismometer to estimate the noise source direction. We can do the comparison. Yeah, and this method just use a large seismic array in Southern California. And the first step is to do the cross-correlation function, and like this figure, and using the cross-correlation function waveform to do the noise source direction estimation. So, and we compare the first year, the 1 year data. So the left figure is from other method, and the right figure is from a 60-point measurement. We can find the mainly come from 225 degrees, and yeah, and it is consistent. And if we look at the longer period, and also the winter also mainly come from the north part of Atlantic and Pacific Ocean, and in the summer mainly come from the west direction of the Pacific Ocean. Yeah, it is perpendicular to the coastline in the Southern California region. So this is just only one single point measurement. And also we can just estimate the local phase velocity based on the single point measurement. So if you look at the below equation, so we use the acceleration, A represents the acceleration and omega represents the rotation. We can do the amplitude ratio. It is the amplitude ratio, it is can estimate the azimuth dependent phase velocity. So if you look at the first figure, it is back azimuth variation in different seasons, and also have the phase velocity variation. If we compare the two lines in the right figure here, so it is the phase measure wheel. And also we want to know what is the phase velocity is really come from the anisotropy model or any other reasons. So we compare the velocity variation in our local anisotropy model. So in the winter, that has a large back azimuth but a smaller phase velocity, and in the summer has a smaller back azimuth and larger phase velocity. So it is match the anisotropy model. So that's why we think the larger velocity variation is because of noise variation. Yeah, it is just one single point measurement. It can provide just limited information on the local on the local seismic anisotropy study. So if we consider one pair of station, what can we do? And we have a theory that is using the amplitude ratio to study the azimuth dependent phase velocity. And also we have another theory that is using cross-correlation functions to estimate the velocity. If we use the cross-correlation function in different back azimuths, we can study the local seismic anisotropy. So this is the map just shows the basic idea. That is, we have first station is a 3-component station, and the second station is 6 station. We can do the cross-correlation, and we do the cross-correlation function ratio we can get the local phase velocity. And in different direction, we can estimate the azimuth-dependent phase velocity. Yeah, and we have to interpret more about the theory. So in principle, in general, the cross correlation technology just using the travel time. Sometimes, in general, they use the travel time to estimate the phase velocity between the two stations. So for the amplitude ratio information, it is a little different from the general method. So if you look at the figure B, if you have two pair of stations in opposite direction and one side source, if you do the cross correlation between the first station and the second station, you can estimate the local phase velocity from 270 degrees. And if you do another pair of station, station 2 and station 3, you also get another phase velocity, but that has the same phase velocity in terms of our method. But for traditional method, they use the time-dependent information that will be different. So this is a difference of conventional compared to the conventional method. Yeah, we also use the array in Southern California. Yeah, small seismic array to retrieve the rotation motion, and we select 3 component station, different direction, and we can calculate the cross correlation. If you look at the waveform, in principle, they should have the same phase, and for the observation, yes, it is. And after we obtain the cross correlation function, we can use the amplitude ratio, like this equation shows. And to estimate the phase velocity, this is a left figure. You can find the phase velocity in the back azimuth domain. And the phase velocity measures the 2% term. It is 2% term. It is anisotropy. Sometimes it is anisotropy term for the Rayleigh waves. Here we just focus on the Rayleigh waves because the loud waves, the amplitude is quite complex. And And if we look at the right figure, the reader line is representing the faster direction from a 6th method. And the orange and the yellow line, it is from other method. And the orange line is the maximum compression stress direction in this region. And the yellow line is the shear wave splitting, using the shear wave splitting to estimate the faster direction, just using the local earthquake, which means it is only sensitive to the upper crust. So our method focuses on the 7 to 12 second. So it is also sensitive to upper crust. So that has a similar and faster direction. And we think it is a stress-induced anisotropy. I have to give a summary, give a conclusion about my presentation. First, if we have a single success station, we can do the microseismic noise source estimation. And it's not only for microseismic noise, but also for other source, I mean the earthquake source or other high frequency source in the urban or other volcano or landslides. Yeah, it is available for other regions. And also the second one, if we have one pair of station, that is we can just using cross correlation function and this technology to estimate the local phase velocity and to do something. Thanks.